Good afternoon, guys. We're bombing along in a early JK with a 10-speed LT1 powertrain. You can see that this Jeep is running about 2,000 RPM at 80 miles an hour, and it feels like it's just idling. We are in a headwind, and you can see that the hood is fluttering. This has got the original rubber hood hold downs, which they had a lot of problems with. I went to the Daystars on my Jeep. They're polyurethane, they're a little tighter, and they keep that hood down. But this is a really clean Jeep. It's a very nice Jeep, and it drives awesome. I often get the question, what kind of mileage can I expect in my conversion? And my standard answer was, you can probably expect the same or better mileage than the V6 if you drive the same. In fact, most of my customers, especially with the larger Jeeps, larger tires, heavier load, more aerodynamic load, all that, are seeing 2 to 3 miles better than the V6, because the V6 has to work so much harder, and there are deficiencies for the larger engine. On the light Jeeps with smaller tires, you're probably not going to notice as much of a difference. But here's the deal. Guys will get a V8 and they'll go out and they'll drive it like a maniac. If you're going to drive your Jeep aggressively with a V8, you're probably going to get the same or worse mileage than the V6. If you drive it the same, you're probably going to see an improvement. And in my experience, 1 to 3 miles to the gallon, based on how heavy your Jeep is and what engine you get and all that. So today I thought we'd talk a little bit about mileage. I can't tell you how much mileage you're going to get out of your Jeep. What I would do is use whatever you're getting before the swap as a baseline. Then if your Jeep is really heavy and you drive reasonably and rationally, you might see 2 to 3 miles per gallon improvement. I guess some guys seeing 4 or 5 miles per gallon improvement. I can tell you on these long drives, and I'm driving to Utah right now, and it's snowing in Utah and it's raining in Vegas, so these aren't the perfect weather conditions. But I can tell you that on the lightly modified Jeeps with 35s or less tires, I usually see the mid to high teens. For heavily modified Jeeps, 40-inch tires, light bars, and all that stuff, I usually get as a low 12 up to about 13, 14. But the average JK drive is probably running about 15, 16 miles to the gallon if I drive 80 miles an hour, which is what I'm doing right now. As I said, there's a lot of variables related to economy. I just had a guy call me up from back east, and he had a turbo put in his Jeep because he thought he would get better economy. And he wanted to know if I went to the V8, would I get a lot better? And I told him no, probably not. And I asked him some questions about his Jeep. First, he went to 1-ton axles, and I asked him to try to push his Jeep. And they said, well, we did try to push it when we were doing the build, and we couldn't, because those axles had so much friction and the tires were grabbing so well that they could barely push this Jeep around a garage. So that is going to equate to less economy on the highway. Second, aerodynamic drag. Just raising your Jeep causes more drag. The Wrangler JK is quite unaerodynamic, especially once you lift it. So you're fighting aerodynamic drag. There's a lot of variables involved what kind of fuel economy you will get. Don't have unrealistic expectations. Guys think they're going to go from a V6 with 40-inch tires getting 9 miles to the gallon to 20 miles to the gallon with a V8. It's just not going to happen. You will see an improvement in most cases, a couple of miles to the gallon here and there, but overall, have your expectations realistic. And that's going to be from the low teens to the high teens. That's where most of these JKs are going to want to be. Now, of course, we got some builds that are pushing 20 miles to the gallon plus on 33-inch tires. They're clean, they're not raised up, they're lightweight, but that's not most JKs. Most JKs have a 3 to 4-inch lift, 35+ inch tires, and stuff hanging off everywhere. And don't forget weight. If you've got armor, steel armor, the average JK has 200 to 300 pounds of armor. That's going to affect accelerating and decelerating. Remember, your brakes are going to have to deal with larger tires, the inertia of the larger tires, just like the engine. And a huge component is, how do you drive? If you drive like a maniac, don't expect good mileage, and that's true for the V6 and the V8. Probably get worse mileage than a V8 though, because you're going to be going faster. But if you drive reasonable and rational, you should get better economy than the V6. Gearing is a big factor. These LTs especially love to be lugged down. They like to be on the highway. Like right now, I'm almost 75 miles an hour at 1800 RPM. That's great. I see guys spinning up 2,500 plus RPM, and some of the V6s 3,000 RPM at 75 miles an hour. You don't need to do that with a V8. These things have long legs. Use that torque. We all know that the smaller displacement engines need to rev up to get into their power band and produce the torque. So that's why you're running those engines at high RPM up these grades with these heavy JKs. The V8s don't need to do that. They have better efficiency because of the extra cubic inches. What kind of gas are you running? Are you running premium gas? Or are you running regular gas? Believe it or not, in some cases, if you run premium, you can get better economy. Because if you were running an 11.5 to 1 or an 11 to 1 compression engine, and you put the premium in, that octane scaler is going to go up and up and up. And I noticed a significant improvement in mileage running the premium than running the regular gas in those higher performance engines. In the lower performance engines with a lower compression, you can get away with the lower grade fuels, but you should always expect some kind of mileage increase by going to the higher octane fuels. What you don't want to do is run a low grade fuel in a high compression engine, because if you do that, then it's just lose-lose. You're going to lose economy and you're going to lose performance. Here we are just outside of Mesquite, and we're going to fill this two-door up. These two doors only hold about 18 gallons versus the four doors 22 gallons. So we put 13 gallons in it. We should be full now. We did use premium, and we're going to hit the road and see what kind of economy we get. We just filled up with gas. It's raining. We're going to head north towards Salt Lake. I do want you guys to notice something. Notice that our long-term fuel trims are pretty high. Now when I let off the gas, they go down. But when you fill up the tank, it resets the fuel adaptives and it changes the pressure in the system. So it's pretty normal to see those up 25-30%, but what you're going to notice as we drive along here, they're just going to start coming down. But guys, I do recommend that you drive monitoring your fuel trims. The long-term fuel trims are very important. I'm kind of bouncing around in this video, but as I think of things I want to talk about, the long-term fuel trims are essentially the culmination of everything in the operating system working well together to come up with that final number. That is how far the computer has to adjust the fuel delivery off of what it predicts it should be, like off of tables. Like Chrysler doesn't run a MAF sensor, MAF, that's mass airflow. They run speed density, so they basically run off of RPM and intake vacuum. GM runs off of RPM and intake vacuum too, but they add a airflow meter or a mass airflow sensor, which gives them better precision to control fuel. So essentially, if this is saying -8, -9, the computer is pulling out -8 or -9% of what it predicts the fuel delivery should be. Now, that number is affected greatly by several variables: altitude, temperature, fuel quality. I get guys go to California, and not just even in Jeeps and regular vehicles, they get that oxygenated fuel, and then they come over here and they switch over to a winter fuel or whatever. But the fuel trims that were learned is so drastically different than what it needs to be that they can start throwing some codes like PO 171, 174, which are the adaptive lean limit was reached, or PO 172, 175, which means the adaptive rich limit was reached. And what that means is the computer either was pulling fuel or adding fuel to the point that it couldn't do it anymore, and that's usually about 30%, 35%. You'll see we're down to about 7 to 8 negative right now. I like to be in the negative slightly, like 2, 3, because I'd rather the computer pull fuel out than add fuel. But this is kind of a complicated theory to understand, but we're going to talk a little bit about stoichiometry and closed loop. A few years ago, I did a video on open versus closed loop, and that can save you a lot of gas. Closed loop on a narrowband oxygen sensor, and I should qualify that. A narrowband oxygen sensor is basically an oxygen sensor that is only accurate at one point, and that's stoichiometric. That happens to be about 0.450, or about a half a volt, that's 450 millivolts, is stoichiometric. And what that means is when the oxygen sensor gets heated up, it can sense how much oxygen is in the exhaust. We all know that we're breathing about 21% oxygen. The rest is nitrogen and some trace elements. A lot of smart guys a long time ago came up with what was called stoichiometry, and they determined that stoichiometric, which is basically the best combination of performance, economy, emissions, and a lot of other things, is about 14.7 to 1 in gasoline. Now that doesn't hold true on alcohol and butane and the other fuels, propane, natural gas. Alcohol is closer to 9 to 1. But what's important here is the content of the oxygen in the exhaust. So if we're breathing 21% oxygen, and if you have an engine that's running good, you should have about 1.5% oxygen come out the exhaust. So it's using most of the oxygen that's available to it during primary combustion. That's called primary air. It's going into the engine through a carburetor or a throttle body or whatever for primary combustion. Now there is secondary air. You've probably heard about secondary air systems. Those systems are designed to complete combustion. What that means is if there's unburned hydrocarbons and COs in the exhaust, we know we have heat in the exhaust. Adding a little bit of air is going to make those burn off before they hit the catalytic converter. But that's not what this video is about. So the oxygen sensor is looking for 1.5% oxygen content in the exhaust, and the computer is using that feedback from the oxygen sensor to control the output of the fuel injectors. Almost all modern fuel injectors are modulated, like a pulse width modulation. Some of the early continuous or CIS systems, the Germans used them. The Bosch system was one of the first automobile fuel injection systems that was popular. They actually put them in the mid-70s Cadillacs. I remember working on those, and they had very primitive oxygen sensors with one wire. Modern oxygen sensors can have 2, 4, 3 wires. They have heaters because oxygen sensors need to be hot in order to work. So when you slow down, you come to a stop, the O2 would go into an open loop condition. And you don't want that. So by adding a heater, you can keep that O2 hot all the time, sensing the fuel trim. When the narrowband oxygen sensor reads about 1 volt, that's full rich. When it reads 0, that's full lean. Now, of course, we're dealing in millivolts, so those aren't absolute numbers. But the bottom line is, when the voltage feedback to the computer goes over 0.450 volts or 450 millivolts, it's going rich. So the computer gives the injectors a lean command. That pulls fuel out. Then the oxygen sensor drops below 0.450 and gives it a rich command. That's the switching of the O2, the up and down that you see. That means you're in closed loop. Like I said, guys smarter than me came up with this a long time ago, that we want to run at about 14.7 to 1. If you hook up a wideband O2, a wideband is a powered O2, and it's not only capable of sensing stoichiometric, but it's capable of sensing above and below stoichiometric. So if you're a racer, you can watch 12 to 1 fuel ratio. If you're a lean cruise guy and you want to get best economy, you could be seeing 16, 17, 18 to 1 to get better fuel economy, and a wideband sensor will do that for you. The narrowband sensor is for production cars that really just want to target one value, and that is stoichiometric, and that's what the law requires. Now, there are some AFS or air fuel sensors, powered sensors in production vehicles. In fact, Jeep did it a while back. I don't know why. Lexus did it. A lot of the manufacturers did it. Maybe they thought they could get some better economy. But we're not going to talk about those. We're going to basically talk about how our JKs work. So the JK works off of the oxygen sensor targeting stoichiometric. Then the output of the injectors are used to control it. And of course, you have all sorts of variables and riders, as I call them: air intake temp, coolant temp, vehicle speed, and a very important sensor is the MAP, or manifold absolute pressure, because that's an indication of load. The lower the MAP, the more load you're under, and when you're floored, wide open throttle, you're basically at atmospheric. Because remember, the engine wants to run under a vacuum, and this column of air in the atmosphere, the lower you get, the thicker it is and the heavier it is. So the MAP sensor senses intake manifold vacuum. So as you open that throttle body up, the intake manifold pressure gets closer to atmospheric. When you're wide open throttle, it almost is atmospheric. Now, there is another sensor called the baro sensor, and a lot of the modern engines run them. Some of the LSs ran them, some of the LTs run them, most of the supercharged engines run them, and what that tells you is what atmospheric pressure is. Because if you're at sea level, it's going to be about 29 inches, but as you go up, it gets less and less and less. So in Las Vegas, where we're at 2,000 feet, we might be at 27. And the engine likes to know that. Now, I've had guys complain with the Pentstars. They'll fire it up at the base of some mountain in Colorado. They'll go up 5, 6, 7,000 feet on the same ignition cycle, and their engine will start running really weird. Well, what's happening is, when you turn the key on, if you don't have a separate baro sensor, it uses the MAP sensor to take a reading of atmospheric pressure. That's what it bases its table on. So as you go up and up and up in altitude, or down and down and down, that reading is going to be skewed. It's not going to be accurate. What the manufacturers recommended early on was just stop about every 3,000 or 4,000 feet, cycle the ignition to get a new reading, and then go on your way. Vehicles that have mass airflow sensors do better because they actually have a real-time airflow calculation, which can take into account actual airflow density. These new LTs actually have a humidity sensor to tell them the water content in this airflow. So the more information the computer has, the better decisions it can make. So if you put pure gasoline in, you're going to be about 14.7 to 1. If you put 10% alcohol in that gasoline, which most of us are running, now you're going to be down about 14.2. If you're running closer to pure alcohol or E85, you might be seeing down in the 9, 10 to 1 range. But the one variable that's not going to change is that 1.5% oxygen content. That's why a narrowband oxygen sensor can be used as a virtual sensor for flex fuel vehicles. Now, it is more accurate to have a hard sensor, but they were really expensive. They're coming down in price, and they are more accurate than depending on the O2. So going back to the closed loop, open loop, the vehicle can't run in closed loop all the time. In a perfect world, maybe it could, but there's situations where you have to have the air-fuel ratio leaner or richer than stoichiometric. One would be starting in the morning. The engine has to be fattened up so that it doesn't stall. So you're in open loop during a cold start. Two would be when you're off the gas. If you're decelerating, there's something called deceleration fuel cutoff, and it cuts the fuel to the injectors when you're slowing down just enough to keep the engine running, because why waste fuel if you're slowing down? That's something that the early carburetors had a hard time with because they had idle transfer ports, and when you slowed down, they were always pulling fuel into the intake, and there really wasn't a whole lot you could do about it. They had dash pots and other things, but it wasn't as controllable as fuel injection. That is an open loop mode, deceleration fuel cutoff. Now here's the big one, performance enrichment. You all have heard of that. What is performance enrichment? Well, when you need power, whether you're climbing a hill, you're towing a trailer, or you're just flat out trying to race somebody, you want to drop that air-fuel ratio down to about 12:1. That's going to give you maximum power. Maybe not maximum efficiency, economy, or emissions output, but it's going to give you maximum power. And I want to say that way back in the 70s and 80s, I remember the arguments over emissions devices, and the manufacturers were required to have the emissions devices bypassed if you needed power, like if you floored it, the EGR valve or air systems would shut down so that they could give you the anemic power that those early engines had. So getting back to performance enrichment, if I'm going to be going up a long grade towing a trailer, I don't want to run it stoichiometric. One, I won't have the power that I want, and two, you don't want the engine to lean out. If you don't put enough fuel into the engine could lean out and damage itself. So performance enrichment has a lot of qualifiers. One would be throttle position. It's usually about 80% accelerator pedal position, but it could also be manifold load. You could be at a light throttle setting with a high manifold load, and you could go into performance enrichment. And then of course there's a whole host of other qualifiers like engine RPM, coolant temp, and all that. So here's what we need to learn about this. A few years ago when I did that video, I often drive between Vegas and Park City. There's a lot of grades as well as high altitude. We hit 6,000–7,000 feet. On average, for every 1,000 feet you go up in altitude, you lose about 3% of your performance. So at 10,000 feet, you're losing 30% of your power. Now, if you've got a JK with a 200 horsepower engine, which only has 100 horsepower at the rear wheels, and you lose 30%, you're like a Volkswagen Beetle going down the road. So performance enrichment is going to help that. What ends up happening is when you go under a heavy load, the computer knows that and it starts putting more fuel into the engine. Well, it can't put more fuel into the engine if it's running closed loop at stoichiometric, because that's fixed at about 14.7:1 with gasoline. So it switches into an open loop mode, just like a cold start, and it starts dumping fuel into the engine. And that's great. Once you get over the hill or the load is gone, you're dropping altitude, you go back into closed loop. But the problem is a lot of guys are right on the edge of closed loop versus open loop, and they don't know it. So what I suggest you do, and I don't have this Banks gauge set up for it right now, but I suggest that you monitor that. Set your gauge up to show closed versus open loop. You can also look at your O2 sensors. So if you see the O2 sensor is flatline rich, like 1 volt, you know you're in performance enrichment if they're not switching anymore. What's nice is when you go down some of these hills, you'll see those O2s flatline lean, and that means it's cutting the fuel off to save you gas. So basically watch that parameter, closed loop, open loop, OL, CL. And if you're going up a hill and you see it go to OL, back off just a little bit and you'd be surprised. Just going from 80 to 78 miles an hour might kick you back into open loop. And when you do that, you're saving gas. And I have had guys call me after they watched that video and say, hey, you know, I've been really conscious about watching that parameter and I picked up a couple of miles to the gallon just by slowing down a little bit some of the time. Guys, you know me, I'm not going to be able to finish this video without going back in time where all this kind of came from. And again, it was pretty much between the wars. During World War I, piston engine technology started to advance rapidly. What was holding them back in World War I wasn't just engine design, but it was materials. The metallurgy, the oils, the fuels just weren't there. By the 1920s, the aircraft industry was really leading the way with internal combustion engines, and they had all sorts of really cool designs. By the late 1920s and 1930s, I think the piston engine was pretty much at its pinnacle. There's nothing new under the sun. There's not a whole lot today that we know that they didn't know with piston engines. They had 4-valve cylinder heads, dual overhead cams, high compression, sleeve valve intakes. They pretty much had it all. And I'm going to try to limit this conversation down to the inline water-cooled engines like the Allisons and the Merlins. The rotary engines were fascinating, and they have a whole story of themselves, but I think the V engines were more akin to what we're doing today. We don't see a whole lot of radial engines in automobiles, although there were some, and there were some in motorcycles too, believe it or not. They had them in the wheel, in the front wheel. I'm going to skip over the early history because I've talked about it before, but by the late 1920s, the Schneider Cup airplanes were looking for more ways to get power. So they made these engines larger and larger, and 1,500 to 2,000 cubic inches was not very uncommon. In fact, the Allison 1700, I think, was the first engine to hit 1,000 horsepower. Now, the goal for them was always 1 horsepower per cubic inch. And you know the story, the racing guys were pushing more than that, 1.25, 1.5 horsepower per cubic inch. But there were some considerations. They could put that power out, but in a fighter plane or a bomber, they had to fly across Europe. This wasn't a short duration thing, like a race of 20 minutes. So by the mid to late 1930s, the writing was on the wall. There was going to be a war, and whoever dominated the skies was going to dominate the war. And countries all around the world invested in airplane engines. Well guys, today wasn't perfect conditions to test fuel economy. We run into a rainstorm. We just went through a snowstorm. We've got below freezing temperatures, and we've got high winds. So we're still going to check this mileage, but in these colder temperatures, I do expect less fuel economy because the engines aren't as efficient when they run this cold. It's pretty much been either raining or snowing since we left Mesquite all the way to Fillmore. It's about 200 miles, and in this two-door you can see we have about 1/4 of a tank left, and we're going to fill up and see what kind of economy we got. Now, we've been running about freezing temperatures. We ran into wind, we ran into rain, we ran into snow. This is the first tank on this LT1, so the adaptives haven't learned. So I'm going to do some more testing on the way back, but there's a lot of strikes against it for economy, and we'll see what it does a little bit down the road when the conditions are more favorable. We've been running about 80 miles an hour most of the time, but in the snow and the rain back there, we did slow down to about 70, 75. So let's take a look at this Banks gauge here. Let's see what data we got. We got RPM, which is pretty much useless because we can see that right there. We're running about 217 degrees. Now remember what I said, these engines like to run warm, the LSs and the LTs, to get better economy. The thinner oils, the tighter tolerances require these engines heat up. Transmission's running at about 138, that hasn't moved in a long time. Our intake temp's at 48 degrees, and we're at 36 outside, so that makes sense. The voltage has been jumping around. It's computer controlled by the GM computer. This is a Gen 5 LT, so you're going to see that go up over 14 and then come back down and go all over the place. You can see the fuel trims did settle. We're running about -4 right now, which is about where I want to see it. I like -2 to -4. That way it's pulling a slight amount of fuel out of it, which I think is better than putting fuel into it. And it is cold out there, so that may change when things warm up. We'll let you know. All right, guys, here we are in beautiful Fillmore. As you can see, some snow built up on the front of the Jeep, which is not a big deal. But I will tell you this, if you've got LED lights and they don't have heaters in them, then you might have a problem in the snow. I can't tell you how many times I've had to pull off the road and clear LED lights in snowstorms because there's no heat. I guess you can add heaters to these, and the incandescent lights or the halogen build up their own heat. But as you can see, this light has got some pretty good snow on it, and I'm going to clean it off because I'm going up towards Park City, and I'm pretty sure we're going to be running into some more snow.